So two things happened when we had to rescale our triangles. One is, the triangles now have different dimensions. Okay, so it's instead of 1, √3, and 2, because we divided each side by 2, we now have this as a 1, 1/2, and √3/2. So the important thing there is the hypotenuse of this triangle is always going to be 1. And now there are still two sizes for the legs, okay? A short one and a long one. The short leg is always 1/2. The long leg is always √3/2, okay? So then the second thing that happened is when I'm trying to find sine or cosine now, I can pretty much ignore the hypotenuse because sine of 30 degrees is just the opposite side, 1/2. Cosine of 30 degrees is just the horizontal side, √3/2. Okay. What we also sort of said, and we've been saying, that sine is associated with the opposite, we know this, and also with the vertical side. And cosine is associated with the adjacent and also the horizontal side. So when you're finding sine and cosine, what you're really trying to do is figuring out a route from the bottom here to the top there, okay? And when I want sine of theta, I want to know how high up do I go for that point. And if I want the cosine of theta, I want to know how much horizontally do I go so I eventually make it to that point, okay? So now if I take this triangle and I put it into the unit circle, all right, the triangle, that vertex intercepts the arc at a certain point. That point has coordinates x, y. And again, being consistent with our sine, cosine, vertical, horizontal, we know that the horizontal side, okay, or the x value is the cosine, and the y value is the sine. So again, my purpose is to see basically the distance or how to get from this bottom point to the top point. And so if I want the sine of this angle 30 degrees, sine is opposite or vertical, so it tells me how high do I need to go to get to that point. Cosine tells me how much horizontally do I need to go over to that point. So now I visualize my triangle. My 30-60 triangle looks like this. The 30 degrees is the smaller angle. It faces the smaller side, right? So I know that going up vertically is going to be less than going over horizontally. Yeah.
Is theta always going to be that angle?
Yes. Yeah. So if I'm looking for the sine of, so if I'm looking at the 30-degree angle, I think to myself, okay, I go over horizontally longer and I go up shorter. That's what we're trying to get at. Now, if I oriented my triangle differently, okay, so I am going to erase some of this to get rid of the clutter. If I oriented my triangle differently so that this is the 60 degree, right? Now, this hypotenuse is still a 1. The sides of the triangle are still 1/2 and √3/2. But what does the vertical side get? Which sides? Which size for the vertical side? 1/2 or √3/2? √3/2, that's the longer one. And the shorter one is here, 1/2. So if my 60-degree angle is here, to go from here to here, I go horizontally a short distance and a much longer distance vertically. That means the cosine, which is the horizontal, is the short side. The cosine is the 1/2. the long side, the sine is the root 3 over 2. Okay? All right? So that's how I always figure out sine, cosine, tangent of 30, 60, 90 triangles, or of 30 degrees and 60 degrees. Yes?
Should we draw that? I don't know how we fit.
With the previous one, so we had the other angle like this, the other triangle like this. That's how it looks.
Okay.
You see that? So the blue here is the 30 and that's the 60. Okay, well, what about the 45, 45, 90? The 45, 45, 90 has two legs of equal length. It used to be 1, 1, and root 2. But we went and divided each side by root 2 in order to make the hypotenuse a 1. So now I have 1 over root 2, 1 over root 2.
Oh, so the goal is always get the hypotenuse equal to 1?
That's the point, yes.
Oh, my bad.
Okay, so now, if I draw a 45, 45, 90 here, and I keep erasing these because I don't want the clutter, but I'll put these back in a minute. Let's draw a 45, let's put that 45, 45, 90 triangle here. Here. So 45, 45, 90. Now, to get from here to here, because it's 45 degrees, I'm going to go the same distance horizontally as I would vertically, right? And what are those distances? 1 over root 2, 1 over root 2. So, if somebody asks me, hey, what is the sine of 45 degrees? Here's what I do. I visualize the unit circle with that triangle, and I say, oh, to go up to this point, I go up 1 over root 2, so that's what it is. 1 over root 2. Okay? All right. Now, let's put all of this together in all their glory, right? We're going to revisit these triangles now. Okay, so look at the unit circle. This is what the unit circle looks like in its full glory. So take a look at this. If this is 0 degrees and 90 degrees, 45 degrees is halfway. This is 30 degrees and 60 degrees. Okay? So it's 30, 45, 60, 90. Okay, now, so suppose somebody asked me for the cosine of 60 degrees. Here's what I visualize. I visualize the hypotenuse at 60 degrees there. So that triangle will look like this, right? 60 degrees is the bigger angle. It goes up higher, right? And I say, okay, cosine of 60 degrees. So I go horizontally a short distance and vertically a longer distance. Because the horizontal is the short distance, I know that that's the 1/2. Why do I know that? Because that's a 30, 60, 90 triangle, and there are only two possibilities for the side. 1/2 and root 3 over 2. Okay? Now, suppose somebody asks me for the cosine of 30 degrees. Okay, I'll try to do that in red. I imagine a 30-degree angle here with its triangle. You see that in the red? You see how they look? The progression of triangles there? So now that's 30 degrees. Cosine is the horizontal, right? That triangle has two possible sides, a 1/2 and a root 3 over 2, right? The longer is root 3 over 2, this is the 1/2. So when I want the cosine of 30, I say cosine is the horizontal. For the 30 degree, the angle is lower, so I go over longer horizontally and up a smaller amount. So this is the longer side, root 3 over 2. Okay? How's that going so far? We're going to do lots with this. So eventually, it's going to be almost like a reflex. Okay, let's do a little bit with the radian. Let's talk about radian a little bit. So let's talk about 30 degrees and 60 degrees. 30 degrees. Okay? You want to convert it to radian. Here's a quick way to do it. You could do times pi over 180, but here's a quicker way to do it. How much is 180 degrees in radian? It's pi. What would you have to do to 180 in order to get 30? Divide by what? You would have to divide by 6, right? Well, if 180 is pi, then that's pi over 6. You see how I do it in my head? 60 degrees, I think to myself, what would I have to do to 180 to get 60? What would I have to divide by? 3. Since 180 is pi, I would have to divide pi by 3 in order to get 60. Okay? 45 degrees. What do I need to divide 180 by in order to get 45? 4. So that's pi over 4. Okay? Okay, now, if this is 30 degrees and that's 90 degrees, then, usually students are good at putting the degrees around the unit circle, right? So you have 120, 150, and so on. So look, the 45 ends with a 5, and then so I have a 45-degree angle here. If I make a 45-degree angle there, it passes through the 135. So it's all of the ones that end in a 5, basically. Then 225, then 315. Okay? So look, all of these are 45-degree angles with the x-axis. Okay? Now, let's look at the 30 degrees for a minute. Here's a 30-degree angle. How do I make a 30-degree angle? It's from the x-axis always. In trig, the x-axis is the important axis. The y-axis always comes second. Okay? It's like, you know how Prince Philip died, so now I feel bad, but this was my example for years. But remember how I don't know if you've noticed, but the Queen of England, she always walks first. And poor Prince Philip would always have to follow 2 steps behind. Did you guys ever notice that? That was a rule. It's the same thing with the x and the y-axis. The x-axis is always the 1, and then the y-axis just kind of follows along, okay? So if I wanted to make a corresponding angle in the second quadrant, it would have to be, again, 30 degrees from the x-axis here, okay? So if this is 180, 30 degrees from that is 150, right? So same thing here, 30 degrees, 30 degrees. How are we doing so far? Okay, now let's talk about radian. 30 degrees we said was pi over 6. Okay, you have to know all of them going around the circle. Okay, all of the corresponding angles. So here's how we do it. Take a look at pi over 6. That's 1 pi over 6, right? There's a coefficient of 1 here. Let's keep increasing the coefficient. 2 pi over 6. Do the 2 and the 6 cancel? Yes. So the 6 goes away, right? So we don't want that. 3 pi over 6. Does the 6 cancel and go away? Yes. Don't want that. 1, 2, 3, 4 pi over 6. That doesn't work either. 5 pi over 6. Does the 6 cancel and go away? No. So that's the next one. Okay. Then 6 pi over 6. No good. 7 pi over 6. Okay, that's a good one. Okay. And then 8 pi over 6. 9 pi over 6. 10 pi over 6. They all cancel. 11 pi over 6 doesn't cancel. That's the next one. And then what's 12 pi over 6? How many pi? 2 pi. So you've completed a circle. Okay? Let's do the 60s. 60 degrees from the x-axis, right there. 60 degrees from the x-axis. Okay? So students are usually okay with the degrees. And then you do the same thing with the 60s, with the pi over 3 now. First one is pi over 3. And then 1 pi over 3, 2 pi over 3. Is that good?
Yeah.
Yup. 3 pi over 3, no good. What's the next one? 4 pi over 3, that's a good one. Here. And then 5 pi over 3 works too. This one's a quick one. And what's 6 pi over 3? 2 pi. Okay? So then the next one is the pi over 4s. Okay? Same deal.
Wait, is this all just the same thing? Just with a different denominator?
Yeah, so one is for the 30, 60, one is for the 30, one is for the 60, one is for... So pi over 4, right? It's 1 pi over 4. 2 pi over 4 doesn't work. 3 pi over 4. 4 doesn't work. 5 pi over 4. And then 7 pi over 4. Until you get to 8 pi over 4, which is 2 pi. Okay. So I would expect that my students just kind of know, right? If I say 5 pi over 3, you should know, okay, 5 pi over 3, okay, it's 1 pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. You should be able to traverse the circle like that. Okay? All right. Let's move along to reference angles. Yay! Okay. A reference angle is necessary for us to be able to evaluate trig functions. So for example, if I want the sine of 540 degrees, I need a reference angle. Okay? All right, so okay, what you need to know about the reference angle is, first and foremost, it's an acute angle. It means it goes from 0 to 90, positive 0 to 90. Not positive 0. 0 to positive 90. Okay? Or in radian, 0 to positive pi over 2. That's number one. Second thing, that's the angle that lies between the terminal side of an angle and the x-axis. Okay? All right. So here we go. Suppose you have an angle of, I don't know, 50 degrees. Okay, you draw a 50-degree angle. It's right here. It lies in quadrant 1, right? If it lies in quadrant 1, it's its own reference angle. So we don't have to worry too much about it. But basically, it's the distance from here, from the terminal side to the x-axis. Okay? Now, suppose I have an angle of 140. 140 looks like this. Where's the terminal side? Here. The reference angle goes from the terminal side to the x-axis. But where? You have to go to the nearest x-axis. So from here, I can either go to the left or right for the x-axis. But I take the shorter route here to the x-axis. So if this was 140 until here, what's the distance from here to here? 40 degrees. Okay? So the book has all these, and again, I write them to have you cross them out because I don't want you to memorize anything. I just want you to reason it out. Reason it out. Okay, here we go. Suppose you have an angle of like 200 degrees. That's 200 degrees. The reference angle goes from the terminal side over to the nearest x-axis. What's the distance there? So this much is 180, and I have a balance of 20. Okay? Reference angle, if the angle is theta, the reference angle is theta prime. Equals 20. And then suppose I have an angle of 300. Here. Okay? How much more to go over to the nearest x-axis? 60. Okay? All right. So, let's do some reference angle business. Okay. So here it says sketch the angle and find its reference angle. All right, so let's sketch an angle here of negative 150. We start here. Negative means I go down clockwise. 90, 150, we're about here. Okay, so take a look at what I need from you. I need you, let me make that clear. I need you to show me that loop and the arrow. Okay? Otherwise, if you, okay, and then you must show this terminal, this initial side, and you must show the terminal side with those arrows. Okay? So now, what's the reference angle? It's here. How much is the balance there? 30 degrees. So you say theta prime is 30 degrees. Always positive. Okay? Okay. You're going to like the radian a little bit better now. Watch. Okay, let's draw this. 3 pi over 4. I always write it like this. 3/4 pi. Okay, so we start here. We're going to go counterclockwise. I'm going to go 3/4 of a pi. And if it's pi here, right, for pi, if we go all the way there, 3/4 of a pi, which quadrant is it going to be in? First or second? Second. Okay, you're going to just eyeball, okay? It doesn't have to be like exactly there, but if you're in the wrong quadrant, no go, right? We need this. Okay, this is the reference angle here, theta prime. Guess what? Is 3/4 pi, is that fraction reduced? No, it is. 3/4, it's reduced, right? Like it's not like 6/8, right? 3/4 is reduced, right? So theta prime for radian is always this. You take the denominator and just put a pi on top. That's it. Okay? So denominator and pi. That's it. If you think about it, if this was 3/4 of a pi, the full thing is a full pi. How much is the balance? 1/4 of a pi. So it'll always work out that way. Okay. Now finally for the big idea that we're doing this for. Now we can actually find sine, cosine, tangent. We can find the trig values of any angle that comes our way. It's a 3-step process. First, find the reference angle. Evaluate the trig function for theta prime. So find, like, the sine, cosine, tangent of the reference angle. Then determine the SIGN sign, plus or minus, based on which quadrant the angle lies in. In order to decide that, there is this mnemonic device. All students take calculus. Okay? It doesn't have to be a correct statement. It just has to have the right letters. Okay? So here we go. Here's how it works. Everything is counterclockwise. All students take calculus. Okay? A stands for all are positive. S stands for sine is positive. If an angle lies here, the sine of that angle is positive, cosine and tangent are negative. T stands for tangent is positive. C, cosine is positive. So all students take calculus. If an angle is here, the cosine is positive, everything else is negative. Okay? But also, fine print, their buddies, their reciprocals are also positive. So sine and cosecant, tangent and cotangent, cosine and secant. All right, let's do it. Without further ado, we want tangent of 11 pi over 6. First, let's draw. Let's just figure out where 11 pi over 6 is. This is 11/6 of a pi. How much is 11 over 6 in decimals? 1 and 5 over 6 pi, right? This is the only time I use mixed numbers. So let's draw this. Here we go, starting with the initial side. Here we go, 1 pi, okay? That's 1 pi. And now I need to draw another 5/6 of a pi. Okay, so from here, 5/6 of a pi is almost a full pi. You see that? So there is my 11 and 5/6 of a pi. Okay, you can just put one arrow for yourself, right? Once you get like used to this. I only do that to show you guys. So 11 over 6, that's a reduced fraction. So that reference angle is the denominator with the pi on top. Okay, now, yes, the problem's asking for a tangent of 11 pi over 6, but now I'm going to find tangent of pi over 6. Okay, so look, for pi over 6, right? Pi over 6 is the 30 degree. That's the smaller angle. So here we go. For the smaller angle, the vertical is the small side 1/2. The horizontal is the long side √3 over 2. And what's tangent? Opposite over adjacent. So 1/2 over √3 over 2. 2's go away. So I have 1 over √3. Okay. Next, let's figure out the SIGN sign. 11 pi over 6 lies in the 4th quadrant. So this is all students take calculus. Cosine is positive here, so tangent is negative, right? So I say tangent of 11 pi over 6 is negative 1 over √3. It's not going to take you this long every time, okay? All right, let's do another one. Secant of 270. Okay, let's just see where 270 is. Where is 270? Oh, that's on the quadrantal angle. That's a quadrantal angle. 270 is here. How do I do it if it's a quadrantal angle? It's actually easier. What are the coordinates there? Negative 0, comma, -1. Okay? What's secant? It's 1 over cosine, right? And then what's the cosine? It's, sorry, cosine is x over r, so this is r over x. Okay? That's 1 over 0, undefined. Okay, when I was in high school, and I started taking trig or pre-calc, and we were in this trig chapter, and when we got to this stuff, I remember to this day the feeling I had sitting in class. Everything was so fuzzy. The teacher kept drawing these angles, and she kept drawing these like circular arrows, and she kept, and I'm like, what the hell are you doing? Right? I was just so fuzzy. Now, not so much. But how did it go from, the fuzziness to the clarity? Practice. Practice, practice, practice. The more you do it, the more it kind of sits and grows on you. Okay? All right, so let's do another one. 9 pi over 4. This is 9/4 of a pi. This is 2 1/4 pi. Okay? All right, let's draw 2 1/4 pi. Start here. 2 pi 1/4. Okay? 2 pi and a quarter. Here we go. Reference angle is pi over 4. I just read that, pi over 4. Now, let me find cosine of pi over 4. Okay, pi over 4 is the one where the horizontal and the vertical are the same. So I go over the same amount as I would go up, and that's 1 over root 2, right? So 1 over root 2. Now, in this quadrant, that's all students take calculus, all are positive. Okay, so cosine is positive, sine is positive. So cosine of 9 pi over 4 is positive 1 over root 2. You obviously don't have to put the plus sign. I just do it for like reference. Okay? All right, let's draw negative 300. Negative 300, negative 90, negative 180, negative 270, negative 300 is about here. What's the reference angle there? 60 degrees. Okay, so let me write 60 degrees here. Okay, so now what I want to find is sine of 60 degrees. I don't care that it was a negative angle. The reference angle is positive as far as I'm concerned. So look, 60-degree angle looks like this. Okay? I go up higher than I would go across. So this vertical side is root 3 over 2. So sine is root 3 over 2. In that quadrant, is sine positive or negative? Positive, so the answer is positive root 3 over 2. Okay. Eventually, right? So, like, I wouldn't need to see all this work. Because eventually the idea is for you to be able to do it like this, right? So this is for you in the background, but these are like, you got to get them right or wrong type of things. So eventually, I don't really need to see that much work for these. Okay? It's only for you. Okay, cosine of 120. 120 is not there. 120 is here. So theta prime is 60 again, right? So let me just do it to scale for you guys. Here, so theta prime is 60 again. Okay, now look, I want the cosine. That's the horizontal side. But because theta prime is 60, that's the large angle. The vertical side is the large side. The horizontal is the small side of 1/2. Okay? So that would be 1/2. What about the, like, sine, SIGN sine? Is cosine positive or negative in that quadrant? Negative. Negative, so it's negative 1/2. Okay? All right, let's move on, and then if we have time, we can come back to these. Let me do those other two. All right. Okay, so this is one that we had done previously, a similar one. So we have secant is root 21 over 3. And now it says where sine is positive, find the exact values of the remaining 5 trig values. Okay. So we have an added situation here, okay? All right, so secant is root 21 over 3. Secant is what? It's the cosine, right? It's the reciprocal of the cosine. So where would these angles go here?
Root 21 would be the hypotenuse.
Uh-huh. And then 3 would be here. And so this side here, x, 3 squared plus x squared is equal to root 21 squared. So 9 plus x squared is 29. 21, sorry. Subtract a 9, x squared is equal to 12. Take a square root. X is root 12, which is 2 root 3. Okay, now, you notice how we have two pieces of information here? The secant and the sine is positive. What the heck does that mean? So now we're going to use them together to determine the quadrant. Okay, what does that mean? Yeah, so here I have secant is root 21 over 3. But look, it's positive, right? So this is telling me secant or cosine is positive. So on the unit circle, where is cosine positive? It's positive in the first and the fourth. Okay, now it says sine is also positive. Where is that? The first and the second. When you do this, there's always going to be one quadrant where two items show up. That's the quadrant your angle is in. So my angle is in quadrant 1. Okay? Why does that matter? Because now when I need to find sine, cosine, tangent, I know that they're all going to be positive in that quadrant. Okay? So sine is 2 root 3 over 21. Root 21. Cosine is root 3 over root 20. Why is it? Oh, sorry. 3 over root 21. Tangent is 2 root 3 over 3. And then cosecant, root 21 over root 3. Secant, we already know. Cotangent, 3 over 2 root 3. Okay. Okay, let's see. Oh, look at that. Cosine of 60 is what? This is another more of an honors type question. Cosine of 60 is the same as sine of some other angle. Huh? You're right. Why do you know that? I mean, not why do you know that. How do we know that? Exactly. So cosine of 60 is 1/2. Right? So you ask yourself, sine of what angle is 1/2? 30. Okay? All right. Here we go. This one here, this is another honors type question. This is a big idea that takes us into calculus as well. So look at what this tells us. This tells us that sine of negative theta is 5 over 9. Okay, what the heck is that? Well, let's see. Okay, here's a unit circle. Okay, here is some random angle theta. Where is the sine of theta? It's this, right? Everybody agree with me? Okay. If that's theta, where's negative theta? Yeah. Not the second. So if I start here, where? It's this way, right? Because to draw a negative angle, I go this way, down. So negative theta is down here. Okay? So that is negative theta. Okay. So That's the sine of theta, right? And remember, that just represents a distance, correct? Like that coordinate, like, so, you know, it's the distance from here to here, or it's the value of that y coordinate, right? So the y coordinate there could be a 3. So, you know, the sine of theta could be a 3. I'm just making up that 3. But now for the negative angle, where is the sine? It's here. Well, what's the y value there? -3. Right? So what happens, because sine of theta is the y coordinate, in going from an angle to its negative angle, the y coordinate will switch signs as well, right? Okay, now here's another situation for you. What's another word for negative? What does the negative sign do? Opposite. Negative just means opposite. So, who said theta had to be there? So take a look at this. What if this is theta? Okay? Negative theta is the opposite angle. So where is that? Above it. Okay? But again, if this is the sine, that's the y value. And now this is the sine of negative theta. What happens to the y value? It changes sign. Okay? So, take a look here. If sine of negative theta is 5/9, then what sine of just theta? What would happen? -5/9. And then what's cosecant of theta? -9/5. Okay? All right? Okay.